Okay, good afternoon. Today I will be starting with second module. So in the second module, you have the small signal operation and models of Mosfet, and you will have the first CIE on coming Thursday 13th. Okay, so I'll be sharing the question paper in your WhatsApp group on the particular day and time. And within 1 hour, you have to complete your answers. I mean, write your answers, scan the answer sheet in the PDF format, and upload in the classroom. Okay, so you will have the portions from first module as well as the half of second module. Now we will start with the second module. So in the second module, as I told you, you will have the small signal operations and models of Mosfet. Clear? So here, as you can see from the circuit diagram, here you have a MOSFET which is configured in common source configuration, where the source will be common to both the gate and drain. So this is your source, which is directly grounded, and this is your input side, and this will be your output side. So source is going to be common for both the input and output side. And you can see a DC voltage, capital VGS, and an AC voltage, small letter VGS. So this is what is the notations difference. Okay. So all the AC components, it will be represented by small letter subscripts. Both the subscript and the main letter, it will be small. And if it is pure DC means it will be represented by caps. If it is pure DC means it will be represented by capital letters. Okay. So here we are going to analyze the small signal operation. So to analyze the small signal operation of MOSFET, here we are going to superimpose the AC as well as DC together into this MOSFET circuit. Understood? So both AC and DC we are connecting together. So this is your DC. DC means it is battery, and AC is alternating source. So small letter VGS is represented by the AC component, and the capital VGS, it is nothing but DC. So together we have got both the AC source and DC source. So combined together, and it is given to the input of the MOSFET. Again, this is common source. Why this is common source? Because source is common to both input and output side. And at the output, you are taking at drain. Output you are taking from the drain terminal, and here you have the drain resistance given to the supply voltage VDD. And through the transistor, you have the current flow ID. VD is the output drain voltage. Hope it is clear. So what we are going to analyze, we are going to find the small signal operation and the models of MOSFET. This is the beginning of the second module. Okay. Morning we have completed first module, and now we are going to start the second module. In fact, the first topic is small signal operation and models of MOSFET. Okay. And for your information, I would like to repeat, coming Thursday, you will have the first CIE internals of MEC. So for that, you will have the first module as well as the first half of the second module. Okay, complete first module and the half of the second module. So I'll be sharing the two modules notes along with the recorded videos, whatever I have delivered the classes for you, so that you can make use of.
So what is the date, sir?
Thursday, coming Thursday, 13th it seems. 10th is Monday, no? So it is 13th. Okay, so I'll be sharing the question paper on the classroom, Google Classroom, and you can write the answers in an A4 sheet, scan it, and upload in the classroom itself. Okay, so
So Thursday I have exams, sir.
Yeah, Thursday.
I have exams, sir, internship exam. Viva.
Okay, then you can write Friday, then no problem. Okay.
Okay, sir.
Okay. Thursday at what time you have?
2:30 to 5:30.
2:30 to 5:30. Okay, fine. Okay, then we'll schedule it on Friday. No issues. I will let you know. Okay.
Thank
So this is a small signal operation model of the MOSFET where you have the circuit diagram, and in the circuit diagram you can see both small letter VGS and capital VGS. You should know the difference between those two. The difference is small letter VGS is AC. So this is your AC signal. This is your DC signal. And if you come to here, since you are going to give both input AC and DC together, so now it is going to represented by small letter V with the capital GS. So got the difference between these three. This is fully capital. This is fully small. This will be small letter V with a capital subscript, means it is a combination of both AC as well as DC. So always a pure AC signal will be represented in small letter alone, and the pure DC signal will be represented in capital alone. So here we have given the combined AC and DC. So you have to represent it in small letter V with the capital subscript. Hope it is clear. Okay, so this is what we are going to do. Okay, but both AC and DC signal we are going to give simultaneously to the MOSFET gate terminal. And this is the common source configuration. So by using the circuit, we are trying to analyze the small signal operation of the MOSFET. So in that first we will be analyzing DC bias point. So in this particular topic itself, we are going to have so many subtopics. So the first subtopic is DC bias point, or otherwise known as Q point, whatever we have studied in the earlier module. Now you know the equation for ID, isn't it? This is the equation for the drain current passing through the MOSFET. That is half K n dash W by L into VGS minus VT the whole square. So here, since we are doing the small signal analysis, small signal means we will be considering only DC. Large signal means we'll be considering only AC. Okay. So here we are given only capital VGS. Why we are not taking small letter VGS into account? Because small letter VGS is large signal. Understood? This is large signal and this is small signal. If it is DC means that is small signal, that is large signal. So since in this topic we are dealing with the small signal analysis, here we will be dealing with only DC. DC means pure DC, not AC. Okay, pure DC means only capital letters. So capital VGS minus VT the whole square. Understood? And how we got this particular equation from the earlier module? We know this is a condition for saturation region, isn't it? This is the equation that is satisfying our saturation condition, that is expression for drain current. So now once we have the expression for the drain current, next one is we need to write the expression for the drain voltage. This also we have studied by applying KVL to the outer circuit, output circuit, isn't it? VD equal to VDD minus IDRD. What is VDD? The supply voltage. So when you subtract the drop across the drain resistance, you will have a voltage drop across drain resistance, that's IDRD, isn't it? RD is the drain resistance, ID is the drain current, so the voltage drop is IDRD. So if you subtract this IDRD from VDD, you will get VD. Hope it is clear. VDD is the supply voltage, IDRD is the voltage drop across RD. So if you know, if you have the particular drop, that voltage drop should be subtracted from VDD to get the drain voltage. So that is what is mentioned in equation number 2. These two are very much familiar equations from the previous module. Don't confuse. Okay. Now, next is the condition for the saturation operation. We know that after a particular voltage only we will achieve saturation. The minimum voltage requirement is VGS, at least it should be VGS minus VT. If it is greater than VGS minus VT means that is fine. So this is the equation for saturation operation. Generally it is VDS, but here VDS is equal to VD. Why? Because source is directly grounded. Okay, VDS, it is equal to VD, parallel only. We are taking the drain voltage from drain to source. Source is grounded. So VDS is equal to VD. So instead of writing VDS, now you can write VD greater than or greater than VGS minus VT. That is a condition for the saturation. Okay. So in this way, you are going to fix the Q point. What Q point? DC bias Q point. In DC bias Q point, you are going to consider only DC signals and not AC signals. That is why we have taken all the capital letters into account. So even though in the main circuit, you have both AC as well as DC. How AC is going to represent? AC is going to represent by small letters and DC is going to represent with capital letters. And what about the combination of small and capital? That is AC plus DC. But in the first subsection of this particular topic, we are going to handle with the DC bias point. So if you are studying with the DC bias point, we are interested only in taking DC components. So for that only, we have taken everything in capital, all the voltages. See, the current is capital, voltage is capital. Here also the voltage is capital, isn't it? So everything we have taken in capital letters. So you have to be very careful while writing the small and caps in this particular module. Okay, so in the DC bias point, we are trying to fix the drain current with this respect to this equation and voltage with output voltage with respect to this equation. And what we have to maintain, at least this VT should be equal to VGS minus VT, and for good saturation operation, it should be greater than VGS minus VT. Okay, because unless it is biased in saturation operation, we will not get the faithful amplification process. Coming to the next subtopic of this section, signal current at the drain terminal. Earlier it was DC current. Understood? In the previous subsection, we have dealt with the DC current. So we have put the capital ID only. Now we are going to find the signal current. The signal current means we need to consider the AC current also. Okay. So for that particular thing, we have to consider the total voltage. Total voltage means it is a sum of DC plus AC. How the total voltage will be represented? It is a combination of small letter V with the capital subscript. That is VGS. Okay, small letter V with the capital GS will ensure the combination of DC plus AC. So the total input voltage, which is this voltage, input voltage or gate to source voltage, it is a sum of pure DC voltage and pure AC voltage. Pure DC voltage, it is represented by VGS, and pure AC is represented by small letter VGS. So sum of these two is the total instantaneous VGS. Okay. Now from this, we are going to calculate the total current also. Now you know the expression for the current equation ID. Now see, while writing ID, you have to be careful since you are dealing with the total current, means AC plus DC. Here also you have to put the combination of small and capital. So I should be small and D should be capital, that is AC plus DC. Fine, no?
Yes, sir.
So you know the expression half Kn dash W by L into, previously it was VGS minus VT the whole square in the first case, the DC case. This was the original equation what we studied in the first module. But now we are dealing with AC plus DC. So there will be slight variation. Can you tell what will be the variation? Apart from this capital VGS, there will be small letter VGS also, because we are considering AC together. So the previous equation will now modified as capital VGS plus small letter VGS minus VT the whole square. So this is the equation equal to half Kn dash W by L into. Now this VGS minus VT, I made it together because since these two are DC, I combined these two. Okay, plus small letter VGS I kept here. Just I rearranged, that's all. Now this I will consider as a single term A. This I will consider as another term B. So A plus B whole square is A square plus 2AB plus B square. Very familiar equation from childhood itself. Okay. Now what you will do next? You have to open the brackets, means this half Kn dash W by L should multiply with the VGS minus VT the whole square, plus again this should be multiplied with the second term, again this should be multiplied with the third term. So you are having three terms. That is, you have just opened the brackets. I think it is clear. Now,
Yes, sir.
From this, when you see this term, it is full of capital. You don't bother about this and all. Okay, this is always, it will be there. You just concentrate on the voltage term. These are DC. This is DC. Always a threshold voltage is DC only. Please keep it in mind. The threshold voltage, it will be DC only. So this is going to be DC current. So that will be ID, capital ID. So I have shown here capital ID because this is pure DC. But when you come back to the second term, this is DC, but this what happened? What about this small letter VGS? This is AC, isn't it? So here you have both DC and AC, isn't it? This term is DC, and this term, since it is small letter, it will be AC. And third term, when you can see, this is purely small, so that will be signal. So this is directly proportional to the square of the input. Signal means it is AC. Okay. So it is directly proportional to the square. See here you have a square. So square of the input signal. So that is equation number 5. So got the significance of the three terms. The first term is pure DC. Second term is a combination of DC and AC. And third term is directly proportional to the square root of the input signal. Why input signal? Because VGS is nothing but your input. Now, next what I will do is, I will remove this because this is ID, capital ID. So here we are not considering this current because my topic heading, you can check what is our topic. It is the signal current we are going to write, not DC current. Signal current means only pure AC current. So we are not going to consider this. So only wherever the AC components you are finding, that terms only you are going to consider. Here also you are having one AC term in the second term. Third term also you are having AC term, small letter VGS in both the cases. Here you are not going to find any small letter VGS here. So I am not going to take this term. So you have retained only these two terms. So out of these two terms, again, it is clear that this is very much less than that of this. Squared term is very much less than that of the second term. Directly proportional to square of the input signal. That is very less than that of the second term. But how we can keep this condition? To keep this condition, why we are keeping this condition? Because we need to suppress the effect of distortion. Distortion should not happen. Okay. And why this distortion comes means distortion means noise or the signal will get fade gradually. Okay, so that should not happen actually. So to get rid of this distortion, the square term should be very less. So we have to follow this particular condition. So the third term, it should vanish or it should be less than the second term. And from both the left hand side and the right hand side, you can cancel the like terms. So what are the like terms that you have here? A n dash, W by L, you can cancel from both the sides. So the equation will become VGS by 2. How you got VGS? Here you have VGS square and here you have VGS. So one VGS will cancel from both the sides. So remaining here you'll have one VGS only. So VGS by 2 will be less than capital VGS minus VT. You take 2 to right side. So small letter VGS will be less than 2 times of VGS minus VT. And what is this VGS minus VT? VGS minus VT is otherwise known as VOV, which is overdrive voltage. So small letter VGS is less than 2 times of VOV. Okay, VGS minus VT is otherwise known as overdrive voltage, which we have studied from first module. So this condition we have to maintain. What is the small letter VGS? Small letter VGS is your AC input signal. So whenever you are giving an AC input signal to a Mosfet, the condition that we have to maintain is it should not go beyond 2 VOV. It should be always less than 2 VOV. If you can maintain this condition, then you will not get any harmonic distortions. Okay. So, which is the term corresponding to the distortions here? I have told you first term, second term, or third term, Bhavani. Which term corresponds to distortion? This is DC term. This is the combination of DC and AC. And this is the term corresponding to the distortion. That squared term of AC signal will contribute the distortion. So we need to suppress this. Otherwise, what happens? this ID will continuously change, isn't it? Distortion should not happen to the current, isn't it? So we have to suppress this effect. So to suppress this effect of nonlinear distortion, what you have to maintain? You have to maintain VGS less than 2 VOV. If you can maintain this condition, then the third term will get vanished gradually. The third term will not be in our scenario. So this equation number 5 will contain only these two terms, and this third term I can neglect. Clear? Any doubts?
No, sir. Clear.
Okay. So now I will be rewriting this equation number 5 so that it will become like this. Only first two terms I have taken. Out of this, you can see the first term is full of capital letter. The second term you have capital plus small. So this will be AC and this will be DC. So I can write this as small letter ID because this is AC, isn't it? You
Yes,
have AC here, VGS. So this is DC and this is AC. So DC plus AC will be the total current I with the capital D. Small letter I with the capital D is the total signal current which will have a DC term capital ID, that is nothing but your first term, plus small letter I with the capital D, that's your second term. Now, so all this you can study. Okay, only after practicing writing and practice only you will be able to write the for the exam. Now, from this I'm going to find the transconductance. You know what is resistance according to Ohm's law? Resistance is R, it is equal to V by I, isn't it? And what about the conductance? Conductance is a reciprocal of resistance. Conductance is a reciprocal of the resistance. So you need to take reciprocal. Okay. So when you take the reciprocal, the conductance will be nothing but current divided by voltage. Conductance will be current divided by voltage. So current is ID, voltage is VGS. Current is ID, voltage is VGS. Okay. Transconductance means output current divided by input voltage. Which is output current, drain current, input voltage is VGS. Now how you are going to get this particular equation? This is the equation for this. Okay, transconductance. How we are going to get this is by taking the equation of small letter ID, whatever you have kept in equation number 6. In equation number 6, you have ID and take VGS along with ID. If you take VGS along with ID, it will become ID by VGS, isn't it? So what will be the remaining term? ID by VGS is equal to this term, Kn dash W by L into VGS minus VT. That is what I have written in equation number 8. And what is this ID by VGS? It is nothing but the transconductance, which is represented by GM. So now the transconductance is GM, which I can rewrite as Kn dash W by L into what is this? This is nothing but your VOV. As I have said, overdrive voltage.
Voltage.
So from this, you can expect a question. Derive the equation of transconductance by using small signal analysis and plot a graph. How you can find GM graphically. This is analytical way of finding GM, and this is a graphical approach of finding GM. So this is important. I'll repeat once more. What I have done is, first, I will take care of equation of ID. This is the total ID, which will have effect of both AC and DC. So for that, we will include the effect of both capital VGS and small letter VGS here. I will separate the DC term and AC term, expand A plus B whole square, take the common factor inside, open the bracket, you will get the three terms. First term is DC, second term is DC plus AC, third term here you have the square of signal current, which will contribute to the unwanted distortions. So you have to suppress this. So this should be very much less than that of this. That is a condition to be implemented. Third term should be very much less than second term. And cancel out the common terms, rearrange it properly. then you will get VGS less than 2 OV. This condition is to be satisfied for maintaining less distortions so that third term will get vanished and only two terms will be there. After getting two terms, you can say that out of that, the first term is capital ID and second term is small letter ID. Small letter ID is the AC current, capital ID is a DC current. Sum of this is the signal current. Now from this equation, take VGS to right side. The remaining term is K n dash W by L into VGS minus VT. That is nothing but your ID by VGS. ID by VGS is nothing but output current divided by input voltage, which is your transconductance. And in that equation, you have VGS minus VT, which is otherwise known as overdrive voltage, that is represented by VOV. And this is the final equation for transconductance. Now, how you can find transconductance graphically, they will ask. So what you have to do is, you have to draw the transfer characteristics of MOSFET, whatever we have studied in the previous module. In the previous module, we have studied graphical derivation of transfer characteristics. In the morning, we have studied that. So in the x-axis, you are having VGS, in y-axis, you are having ID, and this is the graph that we are getting. What is the significance of giving drawing this graph? You know that until VT, there is no drain current because your voltage is less than the threshold voltage. So until threshold voltage, you are not getting any sort of current. Okay, it is off. The device is off. There is no channel. Okay. Now the device will switch on or the channel will get induced only when the input voltage is greater than threshold. So whenever your input voltage becomes at least the threshold voltage, your channel is getting induced and the current will begin to flow. So from this point of voltage, when you increase the voltage beyond or greater, the current slowly increases like this. Okay. This is your transfer cara. And in this, you have fixed the Q point. Let Q point be this point. Any of this line in the middle, you fix the Q point. Let that Q point satisfies our saturation condition. Yesterday and today morning class, I told you always you have to fix the Q point in the middle of the DC load line such that it operates in saturation region. So you have to be very careful, very particular about that Q point. It should satisfy the saturation region. Okay. Now what you will do is through this point you will draw a tangent. Clear, Bhavani? First what you have to do? First you have to plot a graph. In that graph, x-axis is VGS, y-axis is ID, and you plot this graph. Can you explain how did you get this graph? Can you explain? Just now I told how did you get this graph initially?
When
That,
input voltage is greater than the threshold voltage, sir,
yeah, very
the
good.
channel
Yes, channel will
the
get
channel
induced.
will get induced. It will slightly go up, sir.
Oh, correct, correct. And after that, what you have to do is fix this point Q. Okay, and this Q point should be in such a way that it should operate in the saturation region and it should be in the middle of the load line. Now, after that, what you have to do is through this point, you have to draw a tangent. This is the tangent, and that is nothing but the slope. The tangent of that, I mean, slope of that particular tangent, that is G. Slope of this particular tangent is Gm. And early in your plus two classes and all, you might have studied how to take the slope of a line. How to take the slope of a line, that is change in y-axis divided by corresponding change in x-axis. That is what is I have shown here. Here y-axis, what is in y-axis? ID. What is in x-axis? VGS. Change in y-axis is delta ID. Change in x-axis is delta VGS. See, what is ID by VGS then? It is transconductance. Earlier we have shown ID by VGS is your transconductance GM. That is what is shown here. So that whatever the tangent that you have drawn at this Q point and you have found that slope is nothing but GM. Okay. So how you can find graphically the slope of a tangent drawn at the Q point of a transfer characteristics is equal to the transconductance. I will repeat, the slope of the tangent which is drawn at the Q point of transfer chara. Okay. Q point that is located in the transfer characteristics, that is nothing but your transconductance graphically. Analytically, that is analytically means equation wise I have done this. This is graphical wise. Okay.
Okay, sir.
Yeah. Now, what about this two swings? This one and this triangle and this triangle. That is nothing but your current and voltage waveform. This is the waveform for the voltage, and this is the waveform for current. That you can mention. No worries. So this is the graphical approach of finding the transient. So this is what is the slope equation. I told you any straight line if you take, you can find the slope of that line. Slope is nothing but change in y-axis by change in x-axis. Change in y-axis is delta ID by delta VGS, or it is can be called as a dou partial derivative. Dou ID divided by dou VGS, keeping VGS equal to that is you are fixed I mean small this VGS at particular voltage. You have fixed the Q point. This means that you have fixed the Q point. At the Q point, you have find the change in slope. That is nothing but your transconductance. So till now we have completed the second subsection. What is the second? What was the second subsection? That is the signal current. First one is DC bias point. The DC bias point we have just written the equation for ID and VD and the condition of saturation. In the signal current, we derived a equation for small letter ID, and from that we have derived the equation for GM both graphically and analytically. Now I would like to complete the voltage gain equation as well today. And you know what is gain? Actually, gain is nothing but the multiplication factor we have given for the input to be amplified. Suppose input is very weak, you don't have enough strength for that input. So what you will do is you will amplify that input signal with a particular factor. That amplification factor is nothing but voltage gain, which is equal to output voltage divided by input voltage. So here we are directly finding the ratio of output voltage to input voltage so that you will get the equation for voltage gain. Understood? So how you are going to find the equation for voltage gain? So I'll be finishing this within 10 minutes. After that, this meeting will expire. And after that, we'll continue in the next class. Probably the next class, I don't know, because Monday, Tuesday, Wednesday and all, we are very busy with our project, your project and internship presentations. Okay. So anyhow, I have completed the first module. So if I have, till now, you have to study, prepare with for your CI. Till where did
Yes,
I
sir.
stop? Yeah, till where did I stop it up? Till that particular topic, you have to prepare for the CIE. And I will share all the notes till date. That is first module I already shared. Second module also I will share. And plus recorded videos of all these 9 hours. Okay, that also you can, so that while studying, you can on that particular video and parallelly you can study. If any doubts, you can clarify with that particular video also. No, so it will be good for you.
Okay, sir.
Classroom only
Yes, sir.
I will upload. No WhatsApp communication will be there. Notes, assignments, quiz, question papers, then your CIE question paper, video recordings, everything I will be updating in the classroom.
Okay, sir.
So, so this was the equation for output voltage, as you know, and you can see this is the combination of small and capital. Why? Because here both AC and DC I am giving. Here also this is I with the capital D because both AC and DC I am giving. So later on, what I'll do is I'll substitute this small with the capital D, which is equal to capital ID plus small ID, because this is AC plus DC. AC plus DC is nothing but I with the capital D. Okay. So next, what I have done is I have just replace this I with the capital D by capital ID plus small letter ID. And later on, I have opened the brackets. Now from this, I will be taking only this term, not this term. I will be neglecting this term because I am taking AC. This is pure DC. IDRD is pure DC, but I am taking only the signal component. Okay. I'm not taking any DC component for finding the voltage gain. Please keep it in mind that whenever you are trying to find the voltage gain, you will not consider any DC term. So which is a DC term here? Fully capital letter term is DC term. That is capital IDRD is a DC term which you can neglect. So only the remaining time term I have taken. From this, what I did is that is VD is equal to VD minus ID RD. Yeah, this also I have taken 0. This is also pure DC. Understood? VDD is pure DC, that is 0. And this I have replaced it with VD. So this is equation number 10. VD equal to VD minus ID RD. Now, next is the small letter VD is minus ID RD. This is small letter VD because this is pure AC. Okay, this is pure DC. This entire term is pure DC, and for this only I have replaced with the capital VD. Hope it is clear. This is DC, this is DC, this is AC. DC, DC, together it is capital VD. This is AC. So that I have put as small letter VD. Now what is ID? ID equal to GM VGS. How did you get this? Because earlier GM is ID by VGS. Earlier I told you transconductance is a ratio of ID and VGS. So just to rearrange, I have rearranged. So ID becomes GM into VGS. Now put 12 in 11. So VD will become VD will, I mean 12, yeah, VD will become, instead of ID, you will put GM VGS. Okay, so minus GM VGS RD. Directly, I have substituted 12 in 11 instead of ID. That's all. So now you got the equation for output voltage. This is the equation for output voltage, VD. And this is your input. VGS is your input, VD is your output. Hope it is clear. This is your AC input. This is your AC output. I told you for calculating voltage gain, you have only AC. You don't consider any DC. That is why everything it is capital. All the voltage it is now it is I mean small letter. All the voltage signals now it is in small letter. You will not consider any capital letter. Already I have discarded all these things. Okay. So from this I have taken only this term. That only this term, small letter term is small letter VD. And later what I did is I substituted ID with the GM VGS. So there is another small letter term which is input term. That input I will take to left side. Why? Because gain is output by input. Output is VD, drain. From drain only you are taking output now. So output is VD. Input you are giving to gain. So input is VGS. So divide VGS. VD by VGS will become minus GM into RD. This is nothing but your voltage gain. Okay. So that is a final derivation. From this, you can see that you have a minus sign here. The minus sign says that your voltage amplifier is a inverting amplifier or it is providing 180-degree out of phase as we have discussed in the view. Okay. That is what you have, yeah, that is what you have to ensure. And this point you can already I have explained that the saturation region is very much necessary for maintaining the amplifier. Now this you can draw this graph. So this is your input signal which is very weak, very small amplitude, and while drawing output what you have to do is VD is your output. While drawing output it should be enlarged and it should be 180-degree out of phase. See how it is being done. See this is going to negative. This is going to positive side. So meanwhile, it should go to negative. See, this it is going to negative. This line it is going towards negative side, but at the same time when you track downwards, this is going towards positive. So this shows that this is inverting. This is 180-degree out of phase with each other. And what about this peak? Yeah, what about this peak to peak? This is GM into RD because this is VD only. VD expression we have already found now. GM into RD, that is AV. And if you multiply with VGS, you will get a VD. So what is VD? GM VGS RD. GM VGS. This is missed here. It is VGS is also there. It is missing. GM RD VGS. That is the output voltage that you got. It is an exact 180-degree phase reversal with respect to the input. So 3 subheadings we have finished here under the small signal operation and models of Mosfet. What are those? First topic was to find the DC bias point. Second topic was to find signal current, and further we have derived the transconductance both graphically and analytically. Then we have derived the equation for voltage gain, whose final this you have to by heart. This equation you have to by heart, minus Gm into RT. And the minus sign signifies that the output is phase reversal of the input, and finally you have to draw the input and output. Okay.
Yes.
Till this you study for the CIE. If any chance of taking class before that 13th means I will continue with another topics as well. But as of now, you study this because the Monday you don't have class, because Monday you don't have class. Tuesday and Wednesday I am very busy. Okay.
Yes.
Yeah. Okay. Thank you.
Thank you, sir.